Right, so I've just got 10 minutes to talk about what this is, and it's completely unrehearsed, so I don't know where this is going to go, but we'll see how we go. So uPyTester came out as like to fill in a need that I had in my last job to do extensive testing on hardware, and what I really wanted to do is I wanted to use the unit test framework that's in CPython, in standard Python, to facilitate all the testing. I wanted to be able to apply labels to each test, so I could just run integration testing or unit testing and split everything up that way. It just made a lot more sense that way. So, but I wanted to, get stimulation and evaluation and bring that out into hardware, but also at the same time keep it all as Python. So both on running on hardware and running on the host sort of PC. Yeah, I just wanted it all to be running Python. So what came out is I developed uPyTester in its infancy. Anyway, long story. So I developed uPyTester to work on both sides. So it works on the PC host, and you synchronize your application up to any one or many Py boards. I've just made them Py boards for now. I mean, it really could go into anything MicroPython, but at the moment, yeah, it's all I've really got. So I'm just validating it with that hardware. And then you can send, just through serialized commands, you can send commands to set pins, basically stimulate and evaluate in different ways, basically any way that the PyBoard can already do. So I'll go through probably the simplest case and the most complex case I've documented so far, just to sort of illustrate what it does. So for the simplest case, I've got a test, just a ping basically, to send a ping through serial to the board, and it just responds back with the value you sent +1. And the code will instantiate a sort of a PyBoard object to based on the PyBoard serial number. So you can have any number and then basically swap them around. Yeah, it really just uniquely identifies the PyBoard by its serial number and connects to that, which is a challenge on its own. And in the test actually sends it a ping with a value of 100. That command can be anything you put onto the PyBoard. I'll show you the code for that in the next example, but this will effectively serialize that, send it over to the PyBoard, do whatever action you want it to do. In this case, as simple as possible, just respond to that request with 100+1. On CPython, so on the host, this will return a receiver function that you can then invoke to get your response, and here we evaluate that the response was the return value was that number +1. We can run it on the PyBoard here. Yeah, so simple as that. I've got another. This one evaluates whether the button is currently being pressed, so it will always fail if you don't press it. So that brings a bit more of the simulation evaluation aspect of it. If I run it again while the button's being pressed, then it passes. So that's fairly simple. But yeah, like I said, I'm just jumping around completely unrehearsed. To configure the PyBoard for this test environment, you run basically just the main command of the library, and you sync files to it and reset it, and that will just force all the file. But basically run an rsync, mount the board, rsync archive onto the device, and then just force reset it. That's important because I'm about halfway through. If I now jump to the most complicated case, which is still really simple, just each one exhibits one sort of stimulation evaluation sort of pair. Right, so this is a reaction timer. So just a bit of a game as well. So it tests your reaction time and passes if it's less than 300 milliseconds. So that does. So the test itself just sends reaction time. So it just invokes a test your reaction time. Now obviously that's not something I've put onto the PyBoard. That's something that you can create in a custom library. So this is also on the host. Oh, it's a bit of a mess. Maybe that's a bad example, but it's basically this is on the host, and when you synchronize it up. Wrong one. So same thing. It'll grab the main library, but then also synchronize a bench library separately onto the PyBoard itself as well. Just straight after it. So when I run this one, it'll run, and as soon as it turns red, press it, and yes, my reaction time is less than 300 milliseconds. Again, unrehearsed. And if I can run it again and just don't press it, then it'll find that the response was none because it timed out. Yeah. So, I've actually got to time that. So this has been. I have used this in a previous example that I actually can't really. It was for a previous job, so I can't show you it. But it was used for an automotive grade sort of product that I basically used this same system to transmit and receive can frames. Those can frames would have cyclic changes, so every 100 milliseconds you have a counter that would count up and then it would sort of roll over. But you could do that all by sending a single request to the PyBoard, and then it would just keep maintain that response, and you could either choose to send that. You could basically set that up a certain way, but then you could stop it at a particular point and then test that the ECU responded appropriately. The easiest example is IOs. Just simply, in this case, I would send a can frame to trigger a particular behavior, and then that behavior had to set something high for a maximum of 500 milliseconds. All that kind of stuff, and that worked really, really well on the PyBoard to expand it over all the number of IOs that this ECU had. It also means I can. Because it's by no means just talking to one PyBoard. It is talking. These tests are talking to a single PyBoard of a particular ID. It could be 20 PyBoards. I don't know what the limit is, but it'll be based on the operating system. Because each time you open one up, it opens up a receiver and it turns into a thread. So you can do all this asynchronously as well. It doesn't work very well because the code's quite messy. But and synchronously, it's much easier to debug. Which brings me to my next point and my final point. One really good thing about this is also that the code can be terrible. Because what this has done. So what I've just done is I've sent a. Yes, it did. So I've sent the original ping command, which takes the value you sent it and it adds 1 to it and then returns it. What I've done is I've sent to it the value ABC, and I've tried to add 1 to that, which does not work. So what that's done is that has identified here that when I've tried to grab the receiver callable to get the response back from ping. So this is basically on the transmission of ping the value ABC to the PyBoard. that's triggered an exception. The PyBoard error exception. And its content gives us the stack trace that the PyBoard sent back, indicating to me that this is exactly what went wrong, and where it went wrong and what went wrong. So it makes it really easy to debug. Because test code is terrible, and it always will be. Yeah, I think. There you go. I did it 10 minutes.
You don't have any questions?
It is very much in an alpha stage. I'd be really interested to know if anyone would be interested to use this, because if I get your feedback now, then that will quite possibly change how it works. These examples they're split up into basic sort of, don't really need anything to get it going, like the turn LEDs on, you press the switch and it passes, that kind of stuff. To the more complicated ones involve, I want to set up this CAN transmission example as an example test case. You might not have a CAN transceiver, but you'll understand that how the code works to actually get that working. But the last stage of examples will be like a sample product. So what I was going to do is just create some random, really simple product here, as in like an Arduino or something. So just not Python, so it doesn't confuse things further. And create a test bench for that pretend product. Just like a garage door opener or something. And that would, that'll extend, that'll sort of solidify anyone's queries of exactly what does a test bench look like. And I also use that to actually test the code in continuous integration.
Oh, thanks, man.
Thank you.